The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register.
Giving the last presentation for this session is Gary Knight. Gary Knight is the Lehigh Technical Service Engineer, and we'll let him go with that. Thank you.
It's nice to be here. What I'm going to do is tell you a story of using Portland-limestone cement, and it mostly is about the Lehigh Leeds plant, which is located on I-20 east of Birmingham towards Atlanta. And hit the down arrow, right? Yeah. And before we just get started, just go through the standards. At the time we did this project, we did it under 1157 HE cement, so it was a high early limestone interground cement, which today would fully meet the 595 1L spec. So I may use those terms interchangeably, okay? And so, keep moving here. So the Leeds plant was built in 1906. It's still there, and you can see how it's the history of the name changes and the ownership. It was originally started out as the Standard Portland Cement Plant. Then it went to Atlas. Then it became the Universal Atlas Cement Plant. And Birmingham is a big steel town, so that's why it was owned by the United States Steel Corporation. And then Lehigh came along in 1980. And it's been under that present ownership now, and now it's really Lehigh Hanson. So in the beginning, this is what it looked like. Okay, some interesting pictures here. This is pre-environmental impact, right? And it's interesting that this plant, in the original plant, was a dry process plant. So that's the meaning of the loss and ignition right there, right? A lot of loss and ignition, and so that's what the plant looked like. These are what the kilns look like. There were 4 original kilns. And if you look way in the back, you can see the material feeders way in the back. You go pointer here? Yeah. Yeah, so way in the back here. Then the next major expansion came in 1938, and I found reprints of this when it was considered to be the most modern plant in the world. And this is what it looked like during construction. You can see the raw mill here. So it was a dual kiln plant, 1938. And then it went, from here it went to a wet process plant, because that was the sign of the times. Everything went wet process. Okay? And so things moved along. So in 1908, and 2008, we decided to improve the plant once again. And at that time, there was a major change in the plant in 1976, and it looked something like this. Okay, so what we wanted to do was to extend the quarry to give the plant an additional 100 years of life. Okay, and to do that we had to relocate a creek, and we'll talk about that. And then we also wanted to add a new silo, a large 20,000-ton silo. So and this is me opening my big mouth here. And I was at a meeting with, under the Lehigh organization, we have the Heidelberg Technology Center, and they're the ones that really, HTC really is the engineering group that does all these expansions in the engineering. And so I made the statement one day in a meeting. I said, why don't we use limestone cement and show everybody how this works? And basically, everybody went, what's that? Because at that time, it wasn't very common, and we just started making it. So we made a case to use the limestone cement. And so So now it would be considered 595 1L under the current specification. So moving along, we had to replace the original silos, which over here you can see they were structurally unsound really, and today we can only put just a little bit of cement in here, otherwise they would fall down. Okay, so and you can see the condition of the silos, and we are very green because we have trees growing out of the silos over here. See, so we're very green. And so to replace this silo with the new silo was around 5,100 cubic yards of concrete. Okay. So now the other project was the creek project, which is actually a much larger project, about 26,000 yards. And so we had a creek that looked like this, and we had to relocate this creek. So, and the original creek came across like this, and the quarry here, we wanted to push the quarry that way. So we had to relocate the creek in a different direction. So I'll talk about the creek project first. So this is what the creek project ended up looking like. See, this is Portland-limestone cement, and it's 60% slag, and I'll talk a little bit more about that later. Okay, so you can build substantial things out of Portland-limestone cement, and you can see we're very proud of our Lehigh locomotive here. Okay, and so the creek comes along the plant and then goes underground. Comes across like this and actually runs aground all the way over here. Used to go around this way, so we diverted the creek around here, and then it exits on the other side. Okay, so it's a fairly substantial project. Okay, and to relocate a creek is no small effort. Okay, and so now the silo. And the silo is very interesting. This was the silo that we were building, and then today when you build concrete cement silos, this is actually 3 silos, so it's a ring inside a ring inside a ring, and it's approximately 240 feet tall, 80 feet in diameter. The thickness of the walls at the base are about 34 inches. Okay, and so most of the photographs that I'm going to show you are the first phase, which brings the silo came up and we went to this inverted cone, and so most of what I'm going to show you is this construction of this part of the silo. Okay. The first thing we had to do is approach the contractor. Okay, and this little graphic here really should be the size of this wall, because that's the amount of pushback we got from the contractor. And so we approached the contractor and we said we would like to use Portland limestone cement and slag. Okay, and he said no, absolutely not going to do this. Okay, and you have to remember now, this is being built on our property. It's being built, we're providing the concrete, Sherman Concrete with Joe Kelly back there. Okay, we're paying for it. Okay, there's no risk to the contractor. He refused to do it. So it got so bad that the job was getting ready to start on a Tuesday, and on a Friday I get a call, and the first call is from the president of Heidelberg Technology Center, and the first thing he says to me is, and I had proposed the slag that we used is wholesome slag. So the first comment was, why, and he used rather strong words, are we using another company's strong word, slag, to build our silo at Leeds? And I said to him, well, what's the reason for replacing the current silos? And he goes, well, they're falling down. And I said to him, well, if you had built these with slag, they would have lasted 100 years. And he goes, and the new ones are going to last 100 years? I said, definitely. He says, good, and he hangs up. So the second phone call was on a Saturday with the contractor. And so the same fellow says to the contractor, now you got to remember now, there's 100 people en route to start this job on a Tuesday. There's this slip forming crews and everybody. And so the question is, and up to that point, the contractor did not want to use the limestone cement or the slag. And so the president of Heidelberg Technology says to the contractor, he says to him, I have a right to give you a change order, and you have a right to give me a cost for that change order. So what I'm going to do is tell you the change order is that we're going to use this limestone cement and we're going to use the slag. And he said to him, do you still want to be the contractor on Tuesday? And so then he said yes. And so from that point on, he was much more on board. Okay. But we still had to do a lot of testing. So, and when you design, this is a huge slip form project, and so strength is really the secondary consideration. What you have to do is design your mix so it slip forms. In other words, the concrete has to be able to sustain itself, okay? And you have to have this huge slip form work its way up. And once you start this, it doesn't stop. The process goes on. So we did a lot of testing, and one of the reasons for the pushback was that the different set times of the limestone, and at the time we were using an 1157 HE, high early cement. And the pushback was that it's going to be much too fast setting. And we said, well, that's why we're going to balance that with the use of the slag. So we did a lot of testing, and I'll run through this. So here we have our Portland-limestone cements, and then we have our slags, and then we did an awful lot of testing with different admixtures. So what we came up with is that we could alter the set times of this mix quite a bit by the use of admixture and the use of slag. So we came along and we did calorimetry to look at this data. We studied this thing to death, okay? So we did lots of studies here with different amounts. Here's 30% slag. Here's 30% slag with different amounts of admixture combinations. So you can see that we came up with that we could very well control the set time of these different mixes. Okay? So, and we found an old consistiometer, which is a precursor to a rheology type of testing. This is actually used for oil well cement, and we did some testing with this, and so we came up with the stiffening. This measures the stiffening characteristics of the cement, right? So we did this testing, and we said, well, you know, through the combination of the limestone cement and the slag and the admixture, we know that we can hit a window, whatever the window we want, we can hit that. So we came along, and the contractor would not accept any of this testing, absolutely none. And he says you have to convince one guy, okay? How do we persuade the contractor? So we had to convince, they had this guy, Sean. Okay, Sean was the man. This is Sean, okay? This guy goes all over the world with this contractor doing slip forms. Been all over the world doing slip forms. And he says to me, if you can convince me that this is going to work, we're going to do this. So the way they do that is they build a box which represents the size of the structure that you're building, the slip form. So this is the same width as the project that you start out at the base. And what we're going to do is you're going to have a load delivered, and you're going to go up about 16 inches, and you're going to wait a half an hour, which that half an hour represents how long it takes to go around the silo and come back. Okay, so that's your lift. That's what they call the lift. And then what you do is you have a second layer go in there, 16 inches, and then a third. And you have this rebar. Okay, this is a $10 million silo, and this is the QC for the silo right here. Okay, Sean comes along with that rebar, and he sticks it in, and he goes, "That's good." He says, "I think that's good." So what they do is they have this terminology where they stick the rebar in, and they go, if it goes down too far, that's called losing bottom. If it starts to rise up on you, that means you're gaining bottom. That means the concrete's stiffening, right? And then you have gaining bottom, losing bottom, and then you have kind of where you want to be. And so that whole thing is when they build the silo, you have to, this is a massive thing. You have to gauge that time. So you can't go too fast, and it can't go too slow. And the other thing is the feed, and you'll see the rebar here. There's the whole deal of supplying material to the silo. So if you gain too fast, which you might think that would be good, you can't get the rebar in the silo fast enough. Okay, and we'll see that. So anyway, we did these test mixes. Here's our Sherman Industries. And here's the box. And so there's the $20 million QC rod, right? And so you put the concrete in, and you vibrate it, and it goes like that, and then you wait. And you stick it in, right? And they take a measurement from here down, and you record that measurement. Of course, we had to look like we knew what we were doing, so we stuck on some thermocouples there. Okay. So again, then you fill this up and you keep poking. Okay. And so you end up with a graph. And so it's this curve that you're looking for. Okay. You're looking for a certain slope there. So you want to see a certain stiffening. Right. So now you come along, and so we did lots of these tests. Okay. And you can see here the combinations are 30% slag. We got here on this job we use Master Builders, 1025, different Doraville. And what we found out is that certain admixtures will control the slope of that line, and certain admixtures will control the position, the delayed set. Okay, so I'll keep moving here. So we did lots of testing, and then once we decided on a mix, we had to have the ability for the foreman to say speed up or slow down. We had to make it simple, go faster or go slower. So they came up, Mr. Kelly came up with this sheet, and we started off with the mix in the middle, and if the foreman on the job wanted to go faster, he called out that mix design, so he could change. And if he wanted to slow things down, he'd go this way, okay? So that's how we handled that. So, had the train come by and make things look good, okay? So we started off on Tuesday, the job starts out, and there was lots of discussion about how sticky the mix was going to be. It was going to be too sticky. They were worried about it getting off. Once you start slipping, can you get that first lift? So what's really interesting is that all the concrete on the job, once it goes into the form, is put in these buckets. It's not put in with a pump, because you can't get the pump through the steel. There's too much going on there, okay, too much congestion. So there's at least 100 guys on this form running around with these buckets, and there's lots of activity here. And so here you can see them dumping it in. So the concrete gets filled in these buckets, and you can see the formwork as they go, and they just dump it in, and they vibrate it, okay? And then it starts to look like that. Now the structure is supported by these columns, and so the concrete just has to support its own weight as it goes up, okay? So you keep going up, and lots of congestion. So the mix had to be able to be vibrated and flow through all those rebar, okay? So here we are. This is the $20 million rod, and they go like this, and he says, "You're doing good." That's all you want to hear is, "You're doing good." Okay. This is the Q. This is it right there. Forget everything else. That's the whole. That runs that whole job. That whole silo is run through how how the concrete feels with that rod. So now you can see we started to lift off here. We start to go up, and there are 3 decks on this. There's a finishing deck, a pouring deck, and then there's the first deck is where they put the reinforcing through. Okay. So, in order to keep the silo from going like this, they have a laser in there, and every once in a while they look at that. They go, "I guess we're straight," okay? Because you don't want the thing to start leaning. That would be bad. Okay. So, and the other thing to think about is that it's just not the concrete activity. It's all the reinforcing, all the ties, all the steel. Everything has to be lifted. And there's quite a bit of scheduling that goes on here. There's huge amounts of materials flowing on this job site here. Okay, and you can see all the see the amount of reinforcement. Everything is color coded. See, everything is color coded. So they have piles of yellow rebar, green bar, all these things. So everything is color coded. Right. So we go along like this. It's Tuesday. Things are going good. Day 2. So now you can see we're starting up. So you can see the 3 layers. This is the layer that once it's come, this is where the finishes, they go through and they just finish it. And they made comments that they were very impressed with how this concrete finished, okay? And the pump pressures that pump this thing up are actually lower than they normally see. So they were very impressed at how all this went on. And by Thursday, the contractor who didn't want to ever do this was inviting his other clients to come see how well this was doing. Okay, so he had a complete 180 turnaround. It was very interesting. So you can see the inside. So this really starts to take on a huge, massive appeal here. It's a huge, huge structure. How am I doing for time? Good. So we're going up here. Everything's sliding up. And I want to show these are little holes, and we'll come back to those holes later. Here's the old silos. That's what we're replacing. It's around the clock. Once it starts, it doesn't stop. Slip forming. Day 3. Now we're really getting. You can see this bottom lower section is very complicated because you got doors, you got lots of things going on in there. Okay, and inside up here they start to put the inverted cone in, which is where the bottom of the silos go. Okay, and that's all that precast was done with the limestone, cement, and slag as well, and the wholesome slag. Okay, so now we're really cooking. Things are looking good. Okay, and you can see our color coding here. This is the station in the back that controls the rate at which the slip form goes up. Okay, and this is the story pole. This is how they know the rates and where they are and what level. So in other words, somewhere somebody's got a plan that says that when you get to 40.8, you're supposed to put this window in, right? So that's how they keep track of that, right? And so this control here is set on a timer, and it has hydraulic pressure. And so what they do is they say every 6 minutes or 8 minutes, whatever the rate is, based on doing that thing, they go pump it up an eighth of an inch. So every 6 or 8 minutes, the whole thing goes eighth of an inch up, eighth of an inch, eighth of an inch. Okay, so that's what controls that. Here's our QC guy. There's the rod, right? He's smiling. That's good. So here we are. You can see all the materials here. Huge, huge material scheduling issues. Here we go. Keep going up. Now you can see the weather's starting to catch up to us here. Inside, it's very nice. For day 4, starts the rain. We're cooking along, and you can see here. This is where the concrete goes. That's where concrete goes, right in here. See? I think we're losing our light here. Right in there. So you can see it's very busy, very busy. And the reason you can't just pump this in is because you have this deck here. All this stuff gets in the way of using just pumping it directly in there. Okay. There's the buggies, right? The other thing is, it's one thing to keep it straight, but you ought to keep it level. And you would think with all the things that we have today, this is what they use is a system of colored water in tubes, and the water just runs around, and they just mark it. And that's how you keep the silo from going like this, you see. So you got to keep it from going like this, and you got to keep it from going like that. And that's all done just with a water level, okay? There's the water levels, and they just kind of keep that on track. So it's pretty basic, you know. We can put people on the moon, but we still use water levels, right? There's the QC team. There's the finishing station. You can see how nicely that's coming up there. So we're really cooking along. And so now we got to the point where we had to install the cones, and you can see the precast cones we're putting in here. You can see how busy that is. So once the slip form gets past this part, when you're slipping the forms, you're actually slipping three circles at one time. So it gets much more complicated. Okay. And so the rate that we had for this, up to that part, we did about 10 inches an hour, which is actually really pretty good for a slip form. And once we get past that part, the rest of the silo went at over 12, 13 inches per hour, which is fabulous. Okay. So we did lots of testing. Here we did our shrinkage testing, and you can see here that the 6 days, this was very interesting where we got into looking at the C-157, whether you cure for 28 days or cure for 7 days, and so we look at that. But in both cases, you can see that here's a 6-day moist cure, 6-day moist cure, and then 27 days. So we started looking at, it makes a big difference as to how you cure your shrinkage specimens. We did a lot of RCP testing, and we are in the very early stages of developing the mix. We looked at using the slag, and we also looked at using silica fume. It's interesting here that to go from 30% slag to 40%, look at where your RCP numbers go. So it's a huge addition. Your RCP slag does very well with the RCP, right? Same thing with our silica fume over here. This is what the mill cert would look like for the limestone cement. Here you can see Our one-day strength for this was the high early, was one-day cubes were like 3,200, which is pretty good for limestone cement. Okay. Our type 2, we make like a GU, coarse ground. The normal GU would be like 2461 is our one day, which is just above. We shoot for just being just slightly above our normal type 1 or type 2 cement. Okay. So here's some conclusion. Here's the finished silo. You can substitute for limestone cements can be used wherever you would use a type 1 cement. Works very well with fly ash, 618 fly ashes. Works well with admixtures because we tried lots of different admixtures and saw no big issues here. Works well in complex structures, very, very well in complex structures. This was a very complex structure, worked very well. And we can produce very durable concrete. Okay. How am I doing for time? Good. A little bit extra thing. We had some other concerns early on. Birmingham got a lot of rain, lots of rain before we started the project. The area actually got flooded. And so this is what the area around the Leeds plant looked like before they started this project, okay? And so when my back is against the silo and I'm taking these pictures and see these holes and they're coming in, they fill in these holes with grout. And I said, why are we doing that? And they said, oh, we think we have some holes in the ground, right? And so we found some early photos of when they did the 1938 expansion, and then they built that plant. The sinkhole was like this. So this is the plant is built on this sinkhole. So here's the original, here's the piles of the original silos, and here's the sinkhole, a limestone sinkhole. Okay. There's a guy sitting there. You see the caissons? These are the caissons under the silos that we were replacing. Okay, so that whole area has huge sinkhole problems. Okay, and part of the cost overrun in this whole project was the foundation for the silo. That was somewhat missed. Okay, and so, and the guy that they said, oh, we have these pictures all the time, but nobody ever asked us for them. So, so you can see the sinkholes here, huge sinkholes in there. And so you can see the plant, when they were building the plant in '38, this was the sinkhole. And it had all got filled in. So all those holes around the new silo were being filled with grout. And I kept saying to myself, oh, I hope I don't see that thing lean over, you know. But so it was a very interesting project. I had cylinders made. We weren't concerned with the strength. We were concerned with how it was going to slip form. And so I had lots of cylinders made. I had the lab break the cylinders every hour. Once they could get the cylinders to the lab, I said, break your cylinders every hour, because I want to know what that concrete is doing every hour, because it was an hour-by-hour project. I didn't care about 7 days, because in 7 days we'd be done. So we wanted to know every hour. So there's our strength gain. So we wanted the strength gain every hour. Okay. So this is a very good project. The other thing that's interesting here is, I can go back. I think I got this slide here. This is a 52% clinker reduction. This concrete, we replaced 52% of the clinker with limestone and slags. So a very, very environmentally sound, sustainable silo. Right? Any questions? Thank you.
Oh, question back here. Did any accelerators were used for this apparatus?
It's very interesting that you talk about that, because the contractor was, because we were using a high early cement, his concern that everything was going to go too fast, and so we concentrated on making things go slower. So that's why we went to 40% slag and Delvo, okay. And what happened was, at the time we built this, we actually do have winter in Alabama, and it got down to like 35, 38 degrees, and so then we decided things were going well, and they were getting concerned that the cold would affect things, so we started using hot water. So we actually wanted to accelerate it that way. And then the contractor saw that his rate of raising the slip form was coming along, he was gaining, right? So at that point he wanted to use the hot water around the clock. But we couldn't produce hot water around the clock. So we did have a little bit of, we did accelerate the mix, so to speak, in a way, you know. But it was a good combination. That combination of the finely ground, high early limestone with the slag worked wonderful. You know, worked really nice. And Joe Kelly over here is the guy who made all the concrete, right? He's responsible. So, all right. Any other questions? Well, thank you.